Hello all, so let's continue with our lecture number 2 now. Lecture number 1 was basics of machine learning. Now we are starting with actual machine learning technique, that is very first is regression techniques. So we'll start, so here you can see we'll start with linear regression. It's very simple model. Then we'll see its two variants. So this lecture I'll mainly focus on linear regression, and if the time permits we'll go to polynomial regression and all this other stuff. I'm not reading it out because some of you might not know, and it might get overload, like what is all these things. So we'll try to focus on this as well as the Python code of this. So let's begin. Now I'll be discussing the gradient descent approach as well. In this there are two approaches, so we'll see all these two approaches and why I am focusing on GD here, because it is also useful in neural networks. So that's why I'm focusing on it. So now let's move ahead. Now you can see here that firstly, but let me just clear everything. Yeah, so you can see that, sorry to change the screen. Yeah, so we can begin again. Yeah, so linear regression, what does it mean? So let's say I have given a data set. Let's say this is my data set and I am given an input x and output y, right? Let's call it small y. It's the usual notation that input data set is given a capital letter and output is given a small letter. So let's say this is some uh, what we can say, let's say these are weights of students in a class. In one class, let's say this is a weight of a student and this is the height. And intuitively we can say that as weight increase, height also increase. You can say that. Yeah, or we can say other way around as well, like if the height is more, the weight is more, so it will be better if we consider this as height and this as weight. Yeah, so just to avoid confusion, let me just write it again, that this is our height, which is our input x, and this is weight. This will be better thing to explain, I hope. I just cook up the example, so sorry for the inconvenience. So we can say that over here, that let me just change the color. Yeah, red will be good, pink. Yeah, so let's say we have some inputs, like let's say our height is 7.5 inch or any unit. Let's say the weight is 50 kgs. Yeah, let's say 7 feet 5 inch, you can say like this, and the weight is pretty much small, I don't know. So okay, but as the height increases, weight increases, so we'll follow that thing, that it will be 60 kg. Then at 9 it will be some 75 kg or something like that. So let's say so on and so forth, we are given like this. So what we have our x and we have our y. So let's say we have plotted this here on some scale. Please don't mind about the scale. So these are just any random number, and this is also any just random number, but this is x and this is y. Now this is what we plotted, that for this value of x, what is the corresponding value of y, we will get this point, and we have plotted this. So this is what we do right now. Now what we want is that we want what linear regression will do actually, that given a future input after our model is being trained, let's say this is our line that we get. So what it will do is that we can say that this is a very simple line, like y equals to mx plus c that we have. Can we say like this? So this line we already know, that y equals to mx plus c will be this line. This will be some slope and there will be some intercept here. And here you can see the slope is positive and there will be some intercept, like intersecting here. This will be the intercept. So after linear regression, what we'll get is this line. Now forget about all these blue points that we have. This is our training data set. Okay. So now forget about all about other things about training data set. After being trained on this data set, on this blue points, we get this pink line. Now any future input, someone will say that, let's say my student has height of 10. I don't know the unit, just 10. Let's say here is 10. What is the corresponding output should be there? And we know that corresponding to, let's say 10 will be somewhere ahead in this line x-axis. Let's say 10 will be somewhere here, and we will see the corresponding point over there. right? Based on this line. The point should be on this line, yeah, this pink line. Just I am extending it for value x value 10. And similarly, we'll get the corresponding value of y, and that will be our output. That is our weight of our student. Easy. So this is what our basic machine learning model is. A linear regression is. Correct? Now what it will do is that actually it will predict. So y hat is y predicted. Now instead of writing, because we might have more number of features, like this is just height, let's say we have one more feature like age of student, then we also something, what else we can take, like how much he does the exercise, yeah, 5 hours a day or 5 hours a week or something like that. So let's say we have more number of features, yeah. So based on that we have more number of features, so that's why I have put it like x1 x2 and so on up till xn. So we have all features. So you can see that n is number of feature inputs. Please don't confuse it. This are number of features, like the exercise in hours that he does, the height in some unit, and age in some number. All these are features. So these are, let's say here we have 3 features, right? But this thing, I mean this one, let me change the color, that this one that we have is total number of data points or instances, data instances total. So total data instances that we have is this, and we'll denote this as m. Let's say we have m number of data instances, and each instance will have n number of features, so this will be n. Here I take 3. First is exercise that a student do in hours, that weekly 5 hours or 10 hours and so on. This is the height of a student, and this is the age of a student, and the entire thing constitute the training data set x now. So this, their x won't be here, so this will be the feature x1, this will be the feature x2, and this will be the feature x3, right? And this entire feature consists of, so this can be considered as matrix now. That's why I'm writing capital X. So notations are very important here. So again, since we have more number of features, we might not restrict ourselves to just mx plus c. That's why we are having some other notations. Like, so here c corresponds to theta naught. Clearly we can say that. Then this will be x1. Let's say it is exercise in hours. Then this is height. And let's say we have x3, which is the age. And correspondingly we have our inputs. And in corresponding to inputs, we have the parameters, that is theta naught, theta 1, theta 2. Now what learning means in machine learning? So learning means we have to learn these parameters, theta naught, theta 1 and theta 2 in our case, because we are considering 3 things. And based on this, because we already know x1, x2, right? So just what we need is theta naught, theta 1 and theta 2. And after getting this, we'll get our line, because here there are 3 parameters, so there will be a line in 3D, right? Or if you have more, it will be hyperplane and so on. So if we consider just 2 parameters, theta naught plus theta 1 x1, then this is same as y equals to mx plus c. This will be our m, theta 1 will be our m, and theta 2 will be our c. So we can say it will be just this line. And this is what we have to learn, that based on this, because this line depends on what? Input we already know. So it depends only on 2 things, intercept and slope. Based on intercept and slope, we can have different lines. Here, we can change it. Even we can change the slope like this or like this or like this. Even we can have very steepest line based on the slope. Correct? So this is what we want here. Now let me just erase some things so that it becomes good here. So what we want is just this line. Correct? Sorry, but consider it a straight line. This is a straight line. Now coming back to our point, so as I told, theta n is the nth model parameter, and xn is the nth input feature. So it is like this: exercise is first feature x1, then x2 is height, and x3 is age. And as I said, n is this number of features. So can I write in vector form? Like, please note that bold letters are vectors here. So can I say that this and this are vectors? So what is theta now? Theta vector is nothing but it consists of everything like theta naught, theta 1, and so on up till theta n, correct? And what this will consist of, it won't consist of theta naught, sorry, and it consists of what, xn or x vector. It will consist of x1, x2 up till xn. But note that this is the x1, 5 hours, 7.5, and let's say age is 20 years. So 5, 7.5 and 20, this will be our xn, x1, x2, x3, correct? Don't confuse it with capital X, that we'll see later on in the next slide. It's the entire training data set, okay, x. So it will be a matrix, total matrix, but just x consists of this vector. So can we say that this can be written in vector form or a compact form like this? It's just nothing but it's a dot product. That because what dot product says? Dot product says that let's say we have theta 1, theta 2 and theta 3, and if we do its dot product with some other vector x1, x2, x3, what we'll get? We'll get theta 1 into x1, theta 2 into x2 and theta 3 into x3, correct? So this is what we get. But you might notice that we also need theta naught here, yeah? So from where we'll get theta naught? So theta naught is a biased term, so you can see that it's the weighted sum of all the input features. So theta 1 x1, theta 2 x2 weighted, yeah, all input features are weighted with thetas, but along with the additional term called x naught. And scikit-learn library that we are going to use in our Python code just in a minute, it implements this theta naught. So we have to add this theta naught here. So in fact we have to add theta naught, so of course we have to add x naught as well, but x naught is 1, you can say. Can we consider here x naught? But x naught is 1, so it doesn't matter if we write or not, yeah? So that's why just theta naught, but we can write theta naught x naught plus theta 1 x1 and so on. And this is what is done in the library of scikit-learn automatically, so we don't have to specify it explicitly, but it is done. Without bias term it's not possible because we can't change the intercept then, and then we are just restricted in the slope. We can just change the slope of line, but line should be like this only. The slope is fixed. The slope we can change, but we can't have this or this. We can, intercept should be fixed, yeah? So this is not possible because we'll restrict ourselves, and that's why we are using the bias term to have more flexibility. In layman terms I can say like this. So let's move ahead. Now next slide, yeah. So let me just clear things, yeah. Now how to train this model? So as I said, training is nothing but finding the best parameters, thetas, which best fits our training data. So which training data? You can see here that this training data, there should be some line that should best fit this, and this is nothing but our training. After training we'll get this line, yeah, which best fits. You can see we can't get a single line which will fit all the points. We can get just a single line, straight line in between. That is, we can say intuitively by saying that yeah, it is best fitting this given data points, correct? So we'll find this parameter by minimizing the cost function. So now what is cost function? So clearly you can see that we know in our training data we have the actual y that we have. Let me have the cursor, yeah. So we have our actual y, and this is our predicted y from the dot product. This is the actual y from our training data. What we do is we take the dot product. So this is the dot product between two. So you can see, as I said, bold, all these are bold things, but this is not the bold, yeah? This is just a value, single scalar value. And of course y hat that we'll get will also be a scalar value because it's nothing but a weighted sum, although it's a dot product, but we know that dot product is, output is always a scalar value. So what we are doing is y predicted minus y that is actual, we are taking the difference between that and we are squaring. So how we'll start? We'll start by random theta parameters, yeah? So we'll initialize all thetas that we have, like based on number of parameters. Let's say we have two parameters, we'll be having theta naught, theta 1 and theta 2. So we'll randomly initialize theta naught, theta 1 and theta 2, and then we'll take the dot product with our x feature, and whatever value we'll get, let's say we are getting the predicted y as 10. Yeah, that is, the weight of a student is 10 kg, let's say that hypothetically, and the actual weight in the training data set corresponding to this input that we have, let's say it's 20. So there is a difference between two. So we'll do this for all the features. So as I said, don't confuse yourself with m and n. So m are total number of training instances. So yeah, total training instances. So we'll do this square difference. We'll take the square error or difference, you can say that, across all the training data points, and we'll also take the average, and that's why it is called mean square error. So the most common cost function for the linear regression, I can say, is mean square error, or you can also take root mean square error. That doesn't matter, because minimizing the root or without root will be the same thing. So now how to minimize this? Now when we have minima in our mind, we can say differentiation, and we'll do the same. So having differentiation, you can see that we'll get, if you will differentiate and have some optimal values of theta. Sorry, let me just plug in. So what we'll get is, let me just continue with this, that the corresponding closed form solution after having this, luckily linear regression is having closed form solution, but not all the algorithms have this, as we'll see in our logistic regression that we don't have any closed form solution like this, and in that case we have to use gradient descent. So but let's not go into that right now. So what we can say, that this is the closed form solution, and this is the theta parameters that we have. So we'll have our optimal line or plane or hyperplane based on number of parameters that minimize our cost function. But note that here x is the entire training data set. So here I'm not writing a small x vector in bold as we wrote like in our this here. This is just one single feature, one single feature vector. Yeah, I am not repeating it again, I hope you all know this. But here you can see this is the entire training data set, that is, it contains the entire matrix of age, then what was else, height, and then hours of exercise or something. Yeah, so this is the entire training data set x. We are taking its transpose, then again it's multiplying, then taking inverse, then again multiplication with x transpose and y, and now y is also, you can see, that is a target training vector containing yi to im, correct? So m is all the training instances. Yeah, so y is also one vector which contains all the actual output from our training data set, y1 y2 up till ym, correct? Now let's have some hands on. Let's code this so that we'll get a better intuition. So getting to our code. Yeah, so now you can see here clearly that I'm just importing numpy and matplotlib. We'll also use scikit-learn as well, but I'm just having this. So what I'm doing is, I'm not taking more number of features, I'm just taking one feature. So what I'm doing is, I'm generating my own data. I'm not using any particular data set, I'm just generating a random data set. So what this will do, just press shift and tab after writing the function, and what this will do is that it will give the random values in a given shape. So in 100 cross 1 we'll get some random values. So let me just write it, that what we are actually getting. So sorry, yeah, now what we want is pencil here, and we are ready to go. So what we are getting here, actually when I printed it, so you can see that this x is just a simple column vector. Okay, it consists of one column and 100 rows, and there will be any random values. Yeah, it doesn't make any sense, but just a random values, 100 random values, and that's it. Now after this, you can see I'm just trying to run everything again. Yeah. So now we have y as well. So now what is y? You can see that y equals to 4 plus 3x. So I'm just taking one single x. Yeah. So what we can say that this is theta naught plus theta 1 and our x total, and then some random noise. So here you can see the difference. This is np dot random n. So this will be some Gaussian noise. You can see the documentation here that it's written as sample or sample from standard normal distribution. Correct? So this will be some noise with mean 0 and variance 1. Correct? So I am even writing here that output is theta naught plus theta 1 x1 and some Gaussian noise, because here we have just one feature. You can clearly notice here that we are just having one single x. That's it. We don't have more number of features, just one single feature x and its output y, x and its output y. It's like that. Now here you can say y. So obviously y will get as 100 cross 1 again. So we are getting some y. Now our task is, so first let me just plot it. So this is what I plotted even in the slides. So I took the image from here only. So you can say that this is the training data set that we have. So I just generated my training data set, that's it, nothing else. And this is a test data set. So we'll see it later that after learning, after training, we'll use this to predict our future values. That now this is my input, what output can I get? Yeah, this is what the ultimate aim of regression. So now what I'm doing is I'm taking from the scikit-learn, I'm just running it because we'll be using xtest later. So from scikit-learn.linear model, I'm importing linear regression. So this will automatically add theta naught and even x naught equals to 1 in our input, and theta naught to our feature vector thetas, the theta. And then what we have to do is to have linear regression, just we have to write linear regression, and I'm just storing it in some linear regression variable, linear reg variable. And this is what this is how we can do training. So don't know why it's coming again. This just we have to write dot fit our input and our output. And after writing this as our input and output, we are done. So this entire code, this much of code will do the training. Now it's time to predict. So after for prediction, I'm using xtest. So I want to predict for 0. I am giving two values, okay? Like I want to predict for, because we just have one input x1, right? Don't confuse it, like x1, x2, x3, there's all were features, but here I just have one thing, x1. Yeah. So our x just consists of single column x1, that's it. So here I am giving two inputs. I want to predict for x0 as well, x1 as 0 as well, and x1 as 3 as well. To avoid confusion, let me just have, okay, I'll take you through just a single value later, but right now consider this is our x test. Now this will predict, so whatever linear regression model that is being trained now, based on that we'll just write dot predict our new values for x test. And now what I'm doing is, this is again the scatter plot, but now I am giving some, beauty to the image, that I'm labeling as well as I'm saying the color is blue and just labeling it. Now I'm also plotting x test and y predicted. So whatever y we have predicted will be our line, because it's a linear regression, and we'll plot it in red color and we'll label it as our predictions. And I'm just giving the axis value, that because our x was 0 to 3, because I took 0 and 3 here, so I just gave the limit. So this is the limit for x and this is the limit for y. So you can see it's from 2.5 to 20. So here it's 20. Yeah, based on just my plot here, I just gave the values here. And legend, so it will have legend. So legend will show what is legend is. and then I'm labeling the axis, and title is giving to the plot, and we are saying plot.show. So let me just run it quickly. I feel it will be better if I'll write the code entirely line by line. Yeah, just let me know in the comment section, and I'll do the same from the next video. So this is the legend, this is just the title, you can see, and these are the labels of x-axis and y-axis. So I'm just giving x and y. Now you can see that we got some best fit line here, correct? Now if we want to see our parameters, that is what are our best parameters, thetas, so how we'll get that? Let us have it. So if I want to have my best fit parameters, we were here, sorry, this is the logistic regression code that we'll see later on. Yeah, so what we want now is, I'll just explain it, that what we want intercept as well as our coefficient. Yeah, that is our theta naught as well as our theta 1, theta 2 and so on. But here I just took x1, so it will be just theta 1. So we should have theta naught and theta 1. So let me run this, and you can see I'm getting intercept, which is nothing but, let me just write here. So this is our intercept, theta naught is 4.011, and theta 1 that I'm getting is 3.02 or 3 approximately. So now let's move towards x test now. Like y predicted, I took two values of x test, it might confuse you. So let me just run the code by taking just single value. Let's say it's 0. I'm just taking 0 and nothing else. Now I'm running it again. Okay, there is some mistake. Okay, I forgot one parenthesis here. So here you go. Okay, we just need one. Yeah, so now I'm running it again, and you can see that I just got y predicted, because our range from 0 to 3, so we can't see here the predicted thing, because we need two things to plot the line. Yeah, so let me just plot that thing, just y predicted here, that what is y predicted, and you can see I just got 4.011, and this is intuitive. Why? Because we know that now my y predicted is theta naught plus theta 1 x1, and we know my theta naught is 4.011 and my theta 1 is 0.32 into x1. Now what I took x1 as 0. Yeah, my x test was 0, so this entire term is 0, and I just got 4.011, and you can see I got it, and which is nothing but our theta naught. Previously what I did was, I took for once x as 0 and other time x as 3, and that's why we got two output. Yeah, so let me just again change to 0 and 3 and see what we are getting. So here I'll change it. Yeah, this is what we had. Let me run it again and again, and you can see we are getting this. So now again I'm plotting y predicted, and this time we'll get two output. So this is corresponding to x equals to 0, I'm getting this value, and corresponding to this I'm getting this value. But previously we didn't saw the line, because in order to plot the line we should have 2 points at least. Yeah, then we can plot the line. Previously it was just a point, and that's why we didn't see the red line, but now we can see. Yeah, and again I'm repeating, this is called the legend. This one, the red shows prediction and blue dot shows getting data points. Yeah, this is how simple scikit-learn library is. Like, this is how Python is simple, we can say, because Python has all those libraries, and like for even for neural network we'll see that we have TensorFlows and Keras and so on. So it makes life simple even to like build the entire giant neural network. So we'll see all this with the total hands-on. So now let's back to our slides again. So now we were here, so we have coded this. Now it's time to see the other method. So this was normal equation method, but the scikit-learn that we saw, it don't use this normal equation method. Actually it uses something else inside. Yeah, but the thing remains the same. Yeah, that we have to predict the optimal values of thetas. But scikit-learn is not using this thing to compute optimal values of thetas. In fact, it uses SVD, singular value decomposition. It is called. It is one mathematical concept in linear algebra, because this is computationally expensive, like taking inverse of entire training data set. Because assume that my training data set is having million number of parameters. Yeah, we just had 100 points. Let's say we have million, so we have to multiply the matrix with million number of things, then taking it inverse and so on. It's expensive, and that's why it uses something called SVD inside. But this is what we don't want to go into. Just we want is that we should know the concept, that how linear regression works. Yeah, and then we have Python at our rescue, that we can just use any library like scikit-learn and we are good to go. Now the second part is, let me just clear things. So second part is the gradient descent. So obviously we'll see that even with using gradient descent we'll get the same results. Yeah, we'll see that. And there are many variants of it, like batch gradient descent, stochastic gradient descent, and so on and so forth. So I think the video is quite a bit longer, so I'll continue with this. Also will code again. So my target of this playlist is to have hands-on of each and everything that we discuss, and I'll do the same in the same lecture. So we'll continue from this point. Stay tuned. Thank you, and I hope you enjoyed the video.